Alright, so let's continue with the left rotation now. So I just started making this, but we'll just start again. So we have public void L rotation. We're using this set of numbers. It's the same set, just shifted around. So the steps are going to be pretty much the same thing, it's just going to be symmetrical. So it's whatever we do to one side, we're going to make it opposite. So let me just pull up my notes here. You can start by creating that method. So this was chapter 20 in the book in Java Foundations. If you are interested in that book, you can check it out. So as I said, everything's just going to be flipped around. So we have a right rotation, we just completed that. So now we'll have a left rotation here. So we'll say a left rotation can be performed at any level of the tree around around the root of any subtree or the root itself. So I mentioned that it corrects an imbalance caused by a left path in the right subtree of the left child. So I think that's a false definition. This textbook has its mistakes. So don't worry about that. We'll just we know what to do. It's just the same thing as this. We're shifting to the left. So if it's a left rotation, we're going to shift it to the right. If it's a right rotation, we're going to shift it to the left. I mean, sorry, if it's a right rotation, we're going to shift it to the right. Apologize. I meant if it's a right rotation, we're going to shift it to the right, and the long path is going to be in the left. So that's what I meant. So here if it's a left rotation, we're shifting the elements to the left because the long path of the elements are in the right subtree. So hopefully that solves any confusion. So here we'll just we'll just start with drawing out the tree again. So we'll just do the little diagram here. So we have 5, 3, 10, 7, 13, and 15. So this is why we shifted to the left, because we have a long path to the right. So hopefully that solves any confusion. The textbook definition was wrong, so that's why I mentioned that. So I apologize for that. So we'll just continue with that. So we have here our long path in the right. This is a degenerate tree because it's not balanced. So we're going to shift the elements to the left using a left rotation. So where did I write the steps last? Oh, I did in the doc, so we'll do it in the doc here. We'll do some Java doc. We'll say make the right child element of the root, the new root element. So we're going to make the right child element of the root, the new root element, just like we did here with 7. We're shifting it over to the left, so we're making a left rotation. So again, the 10, 7, 13, 15 is going to become the new tree. So we'll do the steps in order like last time. We'll go with the code first. So what did we do last time? We created a pointer. But I believe we can just shift the root. So what is it saying? It's saying okay, well, we're going to first shift so it's saying make the right child element of the root the new root element. So we're going to say here root points to root dot get right here. Then the second step is we can create those object reference variables later. So we can say So sorry, let me just see what the next step is. The next step is make the former root element the left child element of the new root. So we'll say here, step 2, with the space. So we'll say make the former root element the left child element of the new root. So we have our tree here. That's initial tree. Here's our step 1. So make the right child element of the root the new root element. Make the right child element of the root the new root element. So we'll say here 10, 7, 13, and 15. So that's step 1 after completing step 1. Then saying make the former root element the left child element of the new root. So make the former root element the left child of the new root. So we're going to put that whole tree over here again. So here we'll create a pointer. Before that we'll say binary tree node of type T. What do we call it last time? Current node. We could say current root. Current root, we'll call it current root this time, so we'll say current root points to root. So we'll set a pointer to the root, we'll call it current root. That makes more sense than calling current node. Current node may work, but since it's a root, we need a distinguishing name. So if we said inner node, that maybe would have been better. So then we're saying make the former root element the left child element of the root. So here we'll say root dot set left dot set left current root. So what it's asking, it's saying make the former root element binary tree node of type T current root. That's our former root. Former means before. The left child element of the new root. So the left child element of the new root. So root was shifted. We're saying root points to root dot get right. Then we're saying root dot set left to current root. Root, which is our new root here, dot set left to current root, which is the whole tree basically. So we're gonna here we're gonna put the tree with the new tree at the bottom. So 10, whoops, so 10, 7, 13. Okay, that's like that. So 10, 7, 13. And we had 15. So here we're setting the left child element of the new root to the former root element, which is this. So we're going to take out 7. This is going to be a little tricky, but we got it here. So we're going to say make the former root element the left, make the former root element. That's the former root. That's our pointer to the root where I highlighted. The left child element of the new root, that's our new root. So we're going to stick that whole tree here. So we'll take the 7 out. We'll say 5. Is that correct? Yeah, so 5. We might run out of space, so I might have to shift these over. So 10, 5. Then 5 has 2 children, 3 and 10. 3 and 10. Then 10 has two children, 7 and 13. Ten has two children, 7 and 13. This part can be a little confusing. Just have to visualize it. Make a diagram. That's probably the best way. 10, 13, and 15. So 10, 5, 3. Sorry, 10. So 10, 13, 15 should be the same. 7's gone because we placed it with this whole tree, so we should see the whole tree here. 5, 3, 10, 7, 13, 15. There we go. So that's the second step. And we'll say the third step is make the left child, so it's going to be the opposite of what we just did before in the other rotation. So we'll say make the left child of what was the right child of the former root. So make the left child of what was the right child of the former root, the new right child of the former root. So we're going to need another pointer here, so we're going to say make the left child of what was the right child of the former roots are right there, I think. So make the left child of what was the right child of the former root. So we're going to say the new right child of the former root. Where's the former root? Former root was 5, so right child should become 7. 7 should go right there. So create a pointer to that inner node. The reason why we do it before is because we want to create a pointer to it before the tree is changed. We'll say inner node points to, so make the left child of what was the right child. Make the left child of what was the right child of the former root. So we're going to say binary tree node inner node points to root dot get right dot get left, right? Because we're going to say the pointer is to the root, then get the right element of the root, and then get the left element, or the left child, sorry. Get the root, then get the right child of the root, then get the left child of that subtree. So there we go, we got a pointer to it now. So then here we'll say, so make that long stuff the new right child of the former root. So the former root was 5. So we'll say root dot get right, nope. So this was, the former root was 5, so root dot get left. Root dot get left dot set right to inner node. Let me just check, that's on the file. Let me just check my notes if that's correct. So we have, this is a left rotation, so we have a current root pointing to our root, or we change it to current from current node. So then here we'll say binary tree node type T, inner node points to current node dot get right dot get left. So we have root points to root dot get right, root dot set left to current root, current node dot set right to inner node, and then return. So that should be correct. We can return if you want to. And that's done. There was a right left and a right left right rotations, but honestly you can just call these methods if you need to. It's going to depend on the tree. So I thought I had a right left and a left right rotations. I have like I have like a recursive method we could do, but it's not really, it's just the same thing, it just does it recursively. So it's like, okay, do you want to balance a tree? And it's like, if you do want a balanced tree, and then it's going to just be a recursive call. If you want to balance the tree again, so I have a brute force balance that uses a basically it just like does a balance of a bigger tree. So take say so after a left rotation, it does an inner left rotation. So what we can do is we can just look at we can just kind of maybe emphasize, because this is a right left rotation, so honestly you can just change it the way you want to. You can balance a tree any way you want to, right? You can do it any way you want to, as long as it works, as I said previously. Because a binary search tree has its nodes like this, so it's like, okay, well, sorry, I should have maybe done the final tree. I should do the diagram of the final tree, so we just did a left rotation. So I'll just do like, okay, well, the final tree is, it's actually just this with the minus a few of the nodes, so we'll take these out. That should be the final tree. Nope, that's wrong. Well, we're saying 10, so 5, 3, 7, so I have to pull this thing up again. So our inner node was, what's up with this? I think I made a mistake. I apologize. I did these diagrams wrong. Did I? No, that's correct. Yeah, never mind, that's correct. So we had a pointer to 7. Right, so it printed 10 twice, and then here we're just going to write 7, I believe. That should be correct, because inner node was, let's just check what inner node was. Inner node was root, dot get right, dot get left. Yeah, so that's 7. So then at the end it says make the former root, which is 5, right child to 7. There you go. So that's right. So we're saying, okay, well, this is a binary search tree. So this is like, okay, well, 10's a root, 5 is less than 10. That's right. 13 is greater than 10. That's right. 3 is less than 5. That's right. 7 is greater than 5. That's right. And 15 is greater than 13. That's correct. So that works. So again, the point I'm trying to make is that you can rotate them however way you want, as long as it works. And you're trying to make it as efficient as possible, so you're trying to use the least rotations. You're not trying to like set pointers to each node, like all 6 of them, and be like, okay, we'll set root, and then set left, set right, and then set left's left, and then set right, left child's right, and then set right child's left, and set child right child's right. That's going to take too long. You just wanted to do it in like 3 steps like we did, maybe 3 rotations, instead of like 6 or more. So that's the goal. You can do them any way you want. Actually, I might just leave it there, because the other way is just taking a tree and just rotating it to work. I'll just check what I did here, but it's really just taking a bigger tree and just making a tree that's bigger, so it has like 4 more elements. So it has 10 elements, and it's going to shift them around. So actually I might have a diagram somewhere. Let's see, what was this called? Called it question 2. So I have a diagram here. See if I can just try to explain a little bit better. Okay, so we have a tree that's much bigger. So it has 10 elements. So we have 13, 7, 15, 5, 10, 3. Do those sound familiar? 13, 7, 15, 5, 10, 3. Okay, then it adds 0, 1, 3. Yeah, so it just shifts them around. We don't really need to get into that. It just really just shifts it around. Like I said, however, you can just shift them however the way you want as long as it works. And you're trying to do it in the least ways possible. So their left rotation is performing, so I can just write it out for you guys. So you can create them however you want. I'll just do here like, I'll do here like public void r left rotation, so right left rotation. And here you can just have like, that's just temporary. Return none doesn't even work. Okay, that's okay. So we just have like some stuff in here, and basically all you have to do here is I'll just write the steps for you. So it's like, okay, so perform. So if the imbalance is caused by a long path in the left subtree of the right child. So let me show you what a tree would look like. That would be using a right-left rotation. So it'd have like 5 here. Maybe I should do it a little farther away. Okay, so we have 5, then 3, 13, 13, is that correct? We have 13, and then we have 10. Whoops. 10. Then we have 15. And then 7. So you can see here the numbers. So this is the long path is here in the right child, and then the left child of the right. So the root's right child, and then that root's the left child. So it's like it's kind of like a long path left here. So it's saying, so the steps to fix this is they don't have steps, they just have this. I'll show you what they have. So it says performing a right rotation around the offending subtree. So it's like, okay, well we're going to shift this, this is here, and we're going to try to shift this element somewhere else. So where are we going to shift this element? Perhaps we're going to shift this element here. Maybe we can try to do this ourselves, so we can say, we can maybe emphasize on this. So performing a right rotation around the offending subtree. Then it says, and then performing a left rotation around the root. That's all that it says. There's no steps like before what to do. So that's our initial tree. What can we do here? Well, we can say, okay, well, we want this tree to be balanced. So what is balance? All leaves have to be within one level, have to be on the same level, or within one level of each other. That's what we said, I believe. I can just double check that, just to make sure, because I closed my notes. So this was chapter 19, I think. So I'll just open this up real quick. No, I do not want to open with Microsoft Edge. God, that thing is so slow. It's like takes like 10 minutes to start up, literally. Okay, so the balanced tree is, a tree is balanced if all of the leaves of the tree are on the same level. So the tree is balanced if all of the leaves, so that's a leaf. Leaf has no children, that's a leaf, are all on the same level or within one level of each other. So are these within one level of each other? No, they're not. This is 2. 3 to 7 is 2 levels away, so that's not balanced. So we're going to balance this. We're going to make them within one level or on the same level. So it says, okay, we'll perform a right rotation around the offending subtree. So that's the offending subtree. So you don't really need to perform a right a right rotation is make the left child element. So maybe we could try it just to see the way they did it. So right rotation, let me just pull these up so I can see them while I'm doing that. Apologize to you because that's too far away. So a right rotation can be performed. Make the left child element of the root. The new root element, so can we just call left rotation on this thing? I think I tried this and it didn't work before. Like I tried to just be like, okay, well, make it call L rotation here, or sorry, call it right rotation. Because there's not enough nodes here. Look, there's only 4 nodes here. And before we had 6, so it's like, okay, so first we're supposed to make the left child element of the root, the new root element. I'll just make a diagram here. So it's really just going to take 5, 3. So here's going to become 10. And then 7. Right? So 13 and 15 are gone at this time, so we're going to need it. Would have needed a pointer there. Then it's saying, okay, well, then perform a left, then make the former root element the new right child element of the new root. Would that work? It might. 13, 15. Okay, then. So that perhaps did work. Make the right child of what was the left child. Make the right child. I apologize here because I just messed it up. So I took our second tree out. So I can't refer back to it. So original tree here, the step was to make the left child element of the root the new root element. Make the left child element of the root the new root element. Is that wrong? I think that is wrong. So we're doing a right-left rotation. Let me just check if that's right. So right, left, left rotation, right, left, performing a right. Performing a right rotation around the offending subtree. Offending subtree. So okay, so no, that's correct. So we're offending subtree. Okay, so had it right here. Just getting a little confused for a sec. So we have offending subtree is so 13. This is our subtree 13, 10, 15, 7. So we're going to take the whole tree here. So we're going to take 5, 3, 13, and then we're saying make the left child. So this is a subtree 13. So make the left child of the root the new root element. So it's just going to be 5, 3, 13 is going to be gone. It's just going to be 10 and 7. Is that correct? I think that is correct. then it's like, okay, make the former root element the right child. The right child element of the new root, so the new root 7. So here we lost, we had 10, so we lost 13 and 15, so it's then, okay, we tag 13 and 15 to the right side of the new root. So there we go, that's our step 3. So that's our step 2 of the right rotation, not the right left rotation. Then make the right child of what was the left child. So make the right child of what was the left child. Make the right child of what was the left child of the form root. So that doesn't exist. That's null. The new left child of the former root. So that I guess that step gets skipped. Now it's just perform a left rotation. So can we just call our rotation here? Then we're performing a left rotation. If that doesn't work, you're gonna have to do the steps again. But it's just the same thing. But that's all that it seems like. Perhaps it might get a null pointer somewhere because of that reason. Let's see. But the thing is, oh no, okay, I know what to do, So we need to, let's get our right-left rotation tree, this one. So we need to perform a right rotation around the offending subtree. So the subtree is 13. So could we say root dot right left rotation? No. Root dot right. We want a right rotation. Yes. Whoops, we want a right rotation. I don't think that might not work because we don't have any parameters. So can we take a root here? Right left rotation, we'll take a, what is a root? Is a binary tree node. Takes a binary tree node, type T, just call it node. So can we say root, or can we say right rotation? Does it take anything? Can we say node root dot right? No. Node dot right. Node dot right rotation. No, that doesn't work, does it? Nope. So I want to perform a rotation on that part of the, I want to do it without hard coding it. So I'm trying to think if, is there a way to do it? There probably is. So we're trying to say, okay, we'll do a right rotation on. Maybe it takes a root. So the right rotation. We'd have to maybe set parameters for these then. That takes a root to do it. So could we say binary tree node of type T root? There we go. Does that work? Binary tree node of type T, call it root. So this one we're saying, okay, we'll do a right rotation on the root. Then here we'll pass in root. And then here we'll pass in, at the end we get our tree here. How many nodes is that in the path? Long path of 4. Is that what we had before? Yeah, it should be fine. So then we should just take a root here. Should work. Okay, so it might not work, to be honest. If it doesn't work, you can just hard code it like we did here to make some new pointers. And we'll just do the opposite, public void left right rotation. Rotation takes a binary tree node of type T root. You could probably make it set up to take a link binary tree if you really want to. Then here we'll just call left rotation, pass in root, and then we'll say rotation. Then here we'll say call right rotation, pass in root. There we go. So we'll set up our tree to test this out. These ones work for sure. So we'll just set up our secondary tree, right, left, yes. So we'll say, okay, we'll go to main. Okay, we'll say linked binary search tree of type integer. We'll call it tree. Points to new linked binary search tree. Pass an integer. That's it. We'll say tree dot add element. So I have to add it up to make sure. I have to add the elements to make sure that it sets it up so that it's a degenerate tree. So can we add 5? What's up with this? So there's no add. Maybe it's called add element. Add element 5. Then we'll say tree dot add element 3. Tree dot add element 13. Tree dot add element 10. Tree dot add element to 15. Then tree dot add element to 7. So let's just do a println here. Actually, no, let's just say tree dot remove here. Let's just pretend we're going to remove something that doesn't exist. Then we'll create a pointer here, save and debug it actually, just to see if our tree looks like our example. Just put a quote there if you hopefully didn't copy me, but whatever that was, not even showing it. So let's just do 15. Not sure if that was the exact number. We'll just try that again. I'm not sure if the parameters is going to work, but we'll try it. It may take me a long time to figure it out. But okay, so we'll do the tree here. Let me just turn my other screen off. It's pretty bright. Put the I'm always using the high contrast. I got some custom colors. I found some really dope colors. It was like looked like a greenish on black. It's pretty sick. That one didn't work though for Office, for Microsoft Word or whatever. It was making the top bar white, and that really hurts your eyes after a while. So I'm using like some yellow ones now. So let's just check here. So we have our tree. Let's just check if that is the right exact tree. So we should have 5 as the root. So we have tree here. And then the roots left is 3. That's correct. Roots right is 13. Roots left should be null and null. They are. We'll say the roots right is, sorry, the roots right, which is 13. Its right should be, its left should be 10. Its right should be 15. 15 should be null and null. Oh god, this thing keeps, if you click, sometimes like drag stuff. So then we'll say, okay, roots 5, 3, and 13. Then 13's left is 10, and its left should just be 7, and its right should be null, so that's correct. So we'll stop that. So what are we going to do here? We're going to say it's going to take a root. So first we're going to say, we're going to call, so this was a right-left rotation, I believe. So we're going to call it right rotation on 13. I think that's what it's going to say, because it says call a, so we're going to call a right, so we're going to perform a right rotation around the fending subtree. So that's around 13, so we'll go to main, we'll say tree dot yeah, I think this is a problem here, because it's now linked binary tree. Because look, if we dot get left, it's linked binary tree. We say dot root dot get there. Now we can try this. Dot get. So we're using the dot operator access our tree to our binary node, because we'll go over it in a sec. So we have tree dot root. So we're saying, okay, tree, and then get the root of the tree. We're saying after we get the root of the tree, get the right, get right, tree dot root dot get right dot get right. Perhaps we're going to put that whole thing in tree dot right left rotation. So tree dot right left rotation, we're going to try that and see if it works. We're just going to run it and see if it worked. Remove element. Okay, so that we're going to delete that. Try that again. Save and run it. I swear I tried this last time, it didn't work. Maybe it did this time, I don't know. So we'll just step in. It might be just a genius magic worked. Because last time I don't remember accessing it, putting this as a parameter. I think I tried to do it with linked binary tree like before. When we said tree dot, it was asking for a linked binary tree, and I'm not sure if I was good with method training yet, so I couldn't really figure out what to put in there. I ended up just doing a brute force method. But if this works, that'll be crazy. I swear maybe I did try it, but I'm not sure, so we'll just check. So we'll say, okay, we'll tree dot. So we're debugging here, so that's not actually going to help. We're going to, let's just say, let's call here, let's say tree dot add element, and we'll just add 100 just to check. So we'll move our debugger a point here, debug point, and then we'll start from there. Oh, whoops, I did as a string, so that's not going to work. We'll just take the quotes away here, then save that and run it. Got news coming up on my screen, I accidentally clicked it. Hopefully the video doesn't stop. Great, I did not want that on my screen. The weather's going to come up now, so hopefully that doesn't stop either. Okay, so we have tree. Okay, so our tree should look like, what should our tree look like? Our tree should be, where are we here? Link binary search tree. So what was our final tree? I don't think I actually posted the final tree. So the final tree should be this. So we'll have 10. So after this, we're going to perform a left rotation, right? Because we have a long path in the right, we're going to move the elements to the left, so we're going to move that 10 over here. Right, then we're going to move these two elements below. So we're going to say 10 if left child is 5 and 13. We may have to hard code it, as I said. But either way, it'll work. This may just be more of an elegant solution. 5, 3, so 5, 3, 7. So we have 10, left child is 5, right child is 13, then 5's left child is 3, 5's right child is 7, and then 13's right child is 15. So it should look like that. So right off the bat we have our root, which is 5, so it didn't, I don't think it actually caught. Yeah, I think I did and try this. So we have 5. So we just wanted to perform a left rotation at the end. So maybe we'll just see what it did look like. So we have 5 here, then we have 3, then we have 13. So then the left child is null and null, and the right child is null and null. Okay, so what happened to our tree? I guess our tree didn't really like that. So we could try to step into it maybe and see what happened. So maybe let's just stop and debug. Yeah, I think I did end up trying that. That's weird that it didn't work though. I think I tried before and it didn't work as well. That's why I did the brute force thing. So we're going to say, okay, we'll tree dot right left rotation. Our root's currently 5. So what does a tree look like initially? So yeah, that's right. We have great. So we have tree. Well, let's just use this. So tree. We have the 5's the root. The left child is 3. The right child is 13. Left should be null and null. Right child should be 10 and 15. Left is 7. Right is null. 15 should be null and null. Yeah, so that's correct. So we'll step in. So we're saying, okay, we'll perform a right rotation on the root. Perhaps the method passing is wrong. So it's saying, okay, we'll perform a right rotation. Nope, that is wrong. Yeah, so we should have said here. So we need parameters for this right-left rotation. Should we need a parameter for this one? I guess so. But it shouldn't be root. It should be root dot get right. That might work better. Then we're saying, okay, then do a left rotation on the root. So maybe we could try that and see if that works a little bit better. There's a null pointer exception on right rotation. So we're saying, okay, we'll do a right rotation on root dot get right. Cannot invoke binary tree node dot get right because the... Oh, okay, so I think I know what's happening here. Because remember one of them, like when we do the initial balance, it was missing 2 elements because look, at this point, remember we had to skip those last few steps because we had to skip that third step that was like make the left child of what was the right child of the former root because we didn't have those nodes. So I think I did end up doing this and I got to that part and it was like, oh well, we don't have those nodes here. So it's going to throw out an exception because it's like, well, how are we supposed to rotate this? We only have 4 elements. Where's the rest? Where does the rest go? So unfortunately, it just doesn't set them to null. It actually throws an exception. So I think this would work. It would work if it has extra elements. So maybe can we add some elements? I'm not sure. If we could possibly try. Is there a better tree? I think I had a tree here, so... So our tree should have had how many more elements? We were missing... At this point we were missing 2 elements. Somewhere we were missing 2 elements, or at least 1. Could we have had maybe 7? Could we have maybe added 4? Because at the end, so let me just try to explain if you're not understanding what I'm saying. I'm saying at the end of when we were doing the right rotation within the right left rotation, so it was like make the right child of what was, let me just copy this. The stupid thing doesn't even go all the way and copy it. So we'll say okay here, so we'll say right here, doing the right rotation. So the last step somewhere was this. Make the right child of what was the left child of the former root. Okay, so we might actually just have to start this again here. So a right rotation can be performed around. So this is our tree here that we're going to fix. So this tree itself should have 6 elements, but it doesn't. So that's the problem here. So it should be like 13. And this one should have maybe a 14. Yeah, so each one should have 6 elements, so that's the problem. Because when we do the shifting, it needs to be actually set. So it's gonna throw a null pointer here because we only have 4 elements here. We should have at least two more. We should maybe have like a 14 here, and then maybe like a 4 here. So we added 14 and 4, so we'll say, okay, is this right? So we say, okay, well, we want to add 14. So is it greater than 5? Yes. Is it greater than 15? Is it greater than 13? Yes. Is it greater than 15? No, so it goes here. We want to add 4 here. Is it less than? Yes. Is it greater than? Yes. Is it less than? Yes. So if that's what we have, it might work, except it still might throw a null pointer. So we added 14 and 4. So here we'll say, okay, we'll add 14. That's the silly thing about their code, their instructions. Tree.add. That's why I had to emphasize. Now I remember why. I probably already did this. So we're adding 14 and 4. Got that in here. What the heck happened there? 13 and 4. So that's what we added here, 13 and 4. Sorry, 14 and 4. 14 and 4, so now we'll try it. How come it didn't give us that exception when we hit run? That's strange, right? Because whenever we did hit play and it did work. That's weird. Let's just hit play and see what happens. Oh, because I think it did work. It just had those elements set to null. So we'll just go here. We'll hit debug and see if it worked. Ultimately, you might just have to hard code it like we did before. Yeah, it's wrong because the root should have changed to 10, so it doesn't work. So you're just going to have to hard code it. So how to hard code it? Well, we're going to take this tree here. So how can we hard code it? Let's just see how we can quickly hard code this. At least we'll do one of them just to give you an example. So we're gonna take our initial tree, 5, 3, 13, 10, 15, and 7. We'll take 4 and 4 out. 14. Excuse me, we'll take that out too. Take the parameters out. Take the parameters out. Take these parameters out. Yeah, I remember changing this around. It's like, oh yeah, well, you didn't give us a full tree to do it. We need more numbers for this to work at the right places. Didn't work. So we're gonna say, okay, we're gonna take these calls out, take these calls out, take these calls out. So what are we gonna do first? Let's take this one out. Stop that, move that down. So we're gonna say, okay, what's the first step? Performing a right rotation around the offending subtree, so right here. So let me just pull up the right rotation steps on here so I can see them. You might want to do the same, or put it somewhere where you can see. So we're just going back to a right rotation. So we're going to make the left child element of the root, the new root element. Make the left child element, so this is the root, we're looking for the subtree, so make the left child element of the root, the new root element. So we're going to say root dot get right. So make the left child element of the root, left child element of the root, the new root element. Maybe I'll just put it here. Make the left child element of the root, the new root element. Make the left child element of the root, the new root element. So it's okay. So it's going to say make the left child of the root right here, the new root element. So we're going to say, okay, well, root dot get right. Actually, no, so we're going to need a pointer here. We could use a pointer, we could just directly shift it. So if we try to directly shift it, let's just see. So make the left child element of the root, the new root element. Yeah, so a pointer would work better, because we're going to be like, okay, well, root dot set right to root dot get right dot get left. That could work. Or we could just here set a pointer. We could say, okay, well, binary tree node of generic type T. We'll say subroot points to root dot get right dot get left. Get left. So binary tree node of type T subroot points to root dot get right dot get left. Then we're going to say, okay, well, root dot set right child to subroot. So step one's done. So what does our new tree look like at this current time? So yeah, it should look like this: 5, 3, and then 10 and 7. So 15 and 3 are gone. So then we'll say the next step is for the right rotation. I'll just do one of them with you guys, maybe, or maybe both, we'll see. Well, maybe I'll come back and do the other one later. So makes the make the former root element the right child element of the new root. So make the former root element the right child element of the new root. So where's the new root? Right here. We should, yeah, so this was, we did a shift. Make the former, so you have a pointer. Do you have a pointer to the old root? Actually, I don't think we do. Binary tree node subroot points to root dot get right dot get left. So yeah, we don't have a pointer to the old root. Maybe we'll change this to new root. Change that to new root, and then here we'll say we'll call a binary tree node of type T to old root or subroot. Old root, maybe. We know we're changing the subroot. Okay, we'll just call it subroot. So subroot points to root dot get right. So we're saying, okay, so make the left child element of the root the new root element. Make the left child element of the root the new root element. So that's what we did. We shifted up here 10 and 7. Then we're saying, okay, well here make the former root element, which is 13. Make the former root element the right child of the new root. So we're going to say, okay, well, root dot set right. We maybe could use some more pointers here, or we could just traverse down from the root again. Because what we're really going to say here is root dot get right dot set right to subroot, right? So that works, or you can create more pointers if it's whatever's most convenient. So now our new tree should be that's the old, so okay. Something's off here. Make the left child element of the root the new root element. Make the left child element of the root the new root element. So we shifted up here. We shifted right here. 10 went up there. 7 got moved there. Then make the former root element which is going to hold that whole thing. Let me take these out because I feel like that's throwing me off here. Final tree we can do later. So we'll say 5, 3, 10, 7. Make the former root element, that's the subroot. The right child element of the new root. So we're saying, okay, well, root dot get right dot set right to subroot. So we're going to put that whole thing here. 13, 10, 15, 7. So 13. Is that correct? I feel like that is correct. Because that will make the former root element the right child of the new root. Because look, these are linked to this old root. So 10 and 15 and 7 are all linked to this subroot here. So when we're saying right element of the new root, which is 10, then we're going to have to tag here all of that. So that should be right. So the last step is make the right child of what was the left child of the former root, the new left child of the former root. So make the right child of what, oops, that needs brackets too. So what is that? Oh great, that thing just went up there. Make the right child. Oh yeah, so this step, it didn't actually work. That's what we were saying. So is there something wrong with this one? There might be. So make the right child of what was the left child. Make the right child of what was the left child. The new left child of the former root. So if we say, okay, well, these are elements here, right? 5, 1, 2, 3, 4, 5, 6, 5, 3, 10, 13, 15, 7. So we have 2 7s. So could we just say, yeah, I think there might be something wrong with this example in itself. I swear it did seem like it did work last time. I mean, like maybe 10 minutes ago when I did kind of imagine it. We're saying make the left child of the root. Make the left child element of the root. The new root element. Make the left child element of the root. The new root element. So yeah, we shifted that here. 10 and 7. And we're saying, okay, we'll make the former root element the right child of the new root. Make the former root element the right child of the new root. Yeah, that's great. Make the former root element the right child of the new root. Excuse me. So we have 10. Yeah, 13 is going to get added here. Then 10, 7, and 15. So that should be right. Five, 3, 10. So now we have double numbers. So we're gonna. Could we just say? So our number. I think our extra numbers are right here. So then could we say root dot get right dot set left to null. Like I said, you might just have to emphasize. That's what I was saying. You might just have to emphasize. You can shift them however you want to, as long as it works. So if that's correct, then we'll take this tree here. We'll set these elements to null. Right. So those were our original numbers, 5, 3, 13, 15, 10, and 7. Yeah, it is. Let me just check the diagram to see if that is our second step. So we have 5, 3, 10, 7, 13, 15. Hey, you know what? That's correct. So actually that's right. So they were missing a step or in the textbook to just set it to null. So that is right. So after that, we'll maybe just say we're done here, and then we'll start something else. So then we'll perform was that what the trees look like initially? We could set them up to maybe take parameters at this point. But I just don't want to really do that and it doesn't work. Because could we just call it right rotation at this point? What was a right rotation do? No, sorry, left rotation. We call it right rotation, right? Then a left rotation. We could try it. So let's just say we'll call a left rotation here. Will it work? We'll see. So we added 14 and 4, did we? So we have 5, 3, 13, 10, 15, 7. We'll get rid of these. And we'll say tree dot add element. Nope, we're not tree dot. Well, yeah, let's just pretend we're adding an element to 100. We'll set a breakpoint. Actually, no, below. Not there. We'll say tree dot right left rotation. Tree dot right left rotation. No parameters. I spell it right. Okay, then here, put a breakpoint, save it, and debug. Hopefully this one works. If not, we'll be here for a while trying to fix it. Subroot. That's set right to so root dot get right and dot set right to subroot without the quotes in there. Okay, that should be that should work. Hopefully, we'll try that. Okay, we have, so the root is 10, the left is 5, the right is 13, left is 3, right is 7, that's right. Right is 13, right is 15. Okay, so it actually did work. So that did work. So I'm sure we could make it we could just call right and left rotation if we just change some of the numbers around. So I think maybe we could do the other one. What do you think? You think you guys could do it yourself, or maybe you want me to help you do it? Let me just have some water. So at least it did work. We've been at this one for 1 hour and 17 minutes. So maybe, excuse me, maybe I could perhaps take a little break and I'll come back. So I'll see you guys in a little bit and we'll finish the rest.